Alrighty, friends, welcome back to our next set of videos here. So we talked about temperature and how that changes in the oceans from the surface down to the deeper waters. And we recall that a lot of the ocean, about 75% of the ocean, is between 0 and 4 degrees Celsius. So pretty freaking chilly. But not to say we don't have colder waters than that, and not to say we don't have warmer waters, but a good majority of the ocean is quite cold. And we've kind of already talked about salinity a little bit, right, when we talked about the chemistry of seawater. And if you recall back to ways that salinity can vary in the oceans, like why can it increase, why can it decrease, things like that. So we're going to talk a little bit more in depth about the distribution of the salinities throughout the oceans. And then all of this ties into what's called the thermohaline circulation. So we're going to actually finally start to talk about how the ocean moves and why it moves. So starting with salinity. So this is a very simplified version of what salinity does as we go down the water column. So we have increasing salinity on our upper x-axis and depth on our y-axis, again with the top part here being where the surface is, and we go down further. So depending on latitude, the salinity may be constant, it may decrease, or it may increase with a depth of up to about 1,000 meters. But below that, below this, the halocline, right, the salinity stays pretty well the same. So we would see most of these variations in the surface waters, and then we would see a pretty sharp either increase or decrease in the salinity values. So in the higher latitudes, the salinity tends to be lower than in the lower latitudes. Again, it kind of just depends on where in the world we're talking about, but this is just an overall simplified version of that. And then if we were to look at the distribution of ocean salinity, this here again is another histogram, but this time instead of temperature, we're looking at the salinity of cubic kilometers of seawater. And about 75% of the ocean is between 34.5 and 35 ppt, which if we remember from our units of salinity, ppt just means parts per thousand. So it would look like the percent, but with a little extra doohickey on the bottom. So pretty salty, which remember 35 ppt is really only 3.5%, which is really wild. It still kind of boggles my mind to this day, but a little bit of salt goes a long way. And that is in regards to the ocean, but also in regards to food as well, right? If we recall our good old, tricks to make your food taste better, just a little bit of salt will go a long way. And if we were to once again look at a slice of the Pacific Ocean with Antarctica over here on the left, so the southern hemisphere on the left, and the northern hemisphere over here on the right, we see the salinity values where the orange means a higher salinity and the blue means a lower salinity. And again, I do not know what incarnation happened with 50-ish degrees north. That's not land. This black one is here though, so maybe just something happened during this transect that happened that just got in the way or something like that. And I meant to say this with the other map when we looked at temperature as well, but I find it very fascinating how we can see the underwater mountains. Obviously, this is incredibly compressed, like the gradients are not this sharp, but it is still kind of a fascinating thing to look at. But what I wanted to kind of touch in on here is where we see at least at the surface, the areas of higher salinities versus lower salinities, right? If we remember our areas of evaporation kind of center around the 30-ish degrees north and south. Remember, that's where our world's deserts are, like the Sahara Desert, the Middle East, the Southwest US. We're all kind of in the same band around the planet. Whereas near the equator, right, if we recall, we have that little thing called the ITCZ, the Intertropical Convergence Zone. And we often see a lot of rainfall with that, a lot of precipitation. So you're adding fresh water into the mix here. Let's see, what else did I want to say? Yes. So even in the lower latitudes, so in the higher latitudes, excuse me. So we have lower salinity going into higher salinity here at the surface. So we have a really intense, where these lines are really, really close together. That is our halocline, right? That really sharp change in our variable here. But we can also see at some point here at about kind of almost like 1,500 meters or 1.5 kilometers, everything kind of mellows out and chills out a little bit in terms of the salinity values. The last thing I want to touch on is something called the density. So all these things combining together will give us the thermohaline circulation, but that's next. So with density, we know that there's changes in these variables in reference to temperature, in reference to salinity, and lastly in reference to pressure, so depth, right? So all of these things combined can control the density of seawater. So density increases as temperature decreases. So colder things are more compact, they're more dense, right? Whereas when we're hot, we're all loosey-goosey, our molecules are floaty-doty all over the place. And the saltier we get, the more dense we get. And then as pressure increases or as we go further down the water column, density also increases. So that's what we see over here on the graph on the right. So density is on our upper x-axis with depth on our y-axis, again with the surface at the top and depth down at the bottom. So we can see that density does indeed increase, but only to a point, right? It's not like it increases exponentially. It eventually does taper off a little bit. So again, this really is trying to drive home this idea that after a certain point, the oceans are homogeneous. They're all the same, which is really fascinating. And then when we think about like the biology of the creatures that live in the deep oceans, like they haven't really had to do a whole lot. They haven't had to evolve much beyond where they're at because they haven't had these changes in environment. If we recall with biology, like evolution happens because something in your environment changed and you have to adjust to it. Well, when you live in a space where not a whole hell of a lot changes, then you're not going to have to make too many bodily changes, which is really quite fascinating. So all of these things combined, temperature and salt and density, give rise to this really beautiful thing called the thermohaline circulation. So this is a density-driven circulation of water masses. So these really slow, deep currents that occur below the pycnocline. And they depend on these density differences, which are caused by temperature and salinity. And this helps transport heat energy across latitudes, which helps affect climate, which is kind of fascinating. We talked a little bit about that earlier in the semester. What's also really fascinating is it allows for movement of oxygen to different parts of the ocean. And I have a cute little video that kind of shows that. If you're familiar with the movie The Day After Tomorrow, which I know I've referenced several times, but the whole premise of this movie is that the thermohaline circulation slows down and stops and just climate disaster happens all over the planet. It's a fun disaster movie, I think, if you're into those kinds of things. So with the thermohaline circulation, it's not meant to be a literal tracing of actual hot and actual cold currents. In reality, it's an averaged out, smoothed out pattern. And it's really just a representation of the overall effect of the movement of warm and cold water. And this driving mechanism for the formation and sinking of dense water is in the polar regions by either significant cooling or an increase in salinity, or it's kind of like an and or sort of situation here. And this density movement moves actually about 90% of the ocean's water. Wind moves the other 10%, and we'll talk about that when we come back actually. So you can kind of think about it as like a global conveyor belt in a sense. So when we cool things down pretty significantly and pretty quickly, think about what would do that. seasons, right? And especially in the Arctic, like we go in and out of seasons pretty quickly. So things would cool down quite fast, and then sea ice would form, which would increase the salinity of the water, right? Because when you form sea ice, you leave the salt behind. So you're creating saltier water, and you're creating really cold water, so that starts this melting, or starts this downward movement and downward process. And that's what this image here is trying to show. So it'd be like up here by Greenland and Iceland, this is where this process begins. And it travels kind of down the mid-ocean ridge in a way, or the mid-Atlantic ridge, excuse me, and then this really cold, salty water just kind of very slowly moves along here. So this particular model is representing some aspects of both surface currents and the thermohaline circulation. So it's taking into account all of these things. And we'll talk about surface currents later on. So I have a couple of visualizations here to kind of help with this idea again, where the equatorial regions over here on the left, polar regions are over here on the right. So we have heating, so we have a net excess or surplus of heat near the equator. We have a net deficit of heat near the polar regions, and so we would start this whole sort of sinking motion near the polar regions, which would then kind of overall spread out here. And then this is just a cute little video showing oxygen movement. So you can kind of see how like these little fish are just caught up in this little current, and it's just, it cracks me up every time. There's no business for this to make me laugh as much as it does, but I just think it's the silliest little thing. So this little, this is not actually how ocean or oxygen is moved through the water, but it's just a really funny little representation showing the bubbles and kind of how currents can be very strong and it's hard to get out. So the last thing that I want to cover in this particular video, and probably actually like just kind of slowing down a little bit as well, is Ekman transport. So there's this guy who was out on an exhibition, and he noticed that, and then they were in sailboats at this time, so they're using their sails. And he noticed that the icebergs were not moving in the same direction that the wind was moving. And that got him thinking, well, what if the water underneath is not moving in the same direction that the wind is moving? So we overall, like Homie came up with this very fascinatingly, but basically water movement overall, the net movement of water is deflected from where the wind is trying to take it. So at the surface, we would see a 45-degree angle from where the wind is blowing to where the actual surface waters are blowing. And then in each subsequent layer, as we go further and further down the water column, friction is at play here. So you have Coriolis and you have friction. So then the overall net transport of water is actually 90 degrees to the right of the wind movement in the northern hemisphere, and it'd be to the left in the southern hemisphere. And I know this might be a little bit confusing, but we'll recover it when we all come back together. But basically, just know that whatever direction the wind is blowing, the overall water underneath that is moving at a 90-degree angle to the right in the northern hemisphere. That's like if we were to add all of these vectors together. And here's just another diagram kind of showing all of this. And it kind of looks like the Fibonacci spiral a little bit, if you're familiar with that. But the idea here again is that the wind is blowing, in this case, to the north, and then the surface current is 45 degrees off center, and then the overall net transport is 90 degrees to the right. If we were to add all of these arrows together, that's what we would get. All right. So again, we'll kind of cover that back together as a class. I know it's a little bit of a confusing topic, but it's all right. And I think that's going to be it, I think, for the videos for this week. There's already kind of a lot going on. So when we come back, we'll talk more about surface circulation. Thanks so much again for your time and attention, and I'll see you on the Flippy Floppy.